Welcome. Purpose of today is to draw Lewis structures for fulminic acid and showing all of its resonance forms. Now this question I believe is a little bit tricky and a bit misleading because we're limited by the tool that we're using. The tool that we're using is Lewis dot structures. Gilbert Lewis in the early 1900s came up with a very simplistic method, but a real powerful one that helped us understand the structures and bond angles of a lot of molecular structures using electrons as point charges or dots. So because we're going to use dots, okay, to determine possible structures that will resonate, okay, we're limited because electrons are what? Really probability waves, okay? These wave functions we're going to treat as dots is going to make us limited in trying to determine all of the resonant forms. We're going to need some data, okay, to really understand which resonant forms or which forms are actually resonating into. But what we can do from these Lewis dot structures is we can determine all the possible structures of these this molecule or these molecules, and determine whether these are the possible ones. Okay, so let's get started with that, knowing full well to understand which are the exact resonant forms we're going to be somewhat limited in, okay, and we'll need some other data. So let's get started and let's write our structure here, a backbone. We're going to have a hydrogen, we're going to have a carbon, we're going to have a nitrogen, and we're going to have an oxygen. Now, understanding that when we do this, we have to look at our atoms here. This is a row 1 element, so it's going to want to bond so that its orbital, okay, or its shell holds a maximum of 2 because it's in the row 1 or period 1. The rest of these atoms are period 2 or row 2 elements. They have an s and a p orbital, and they hold a maximum of 8. And there's our octet rule that Gilbert Lewis came up with. And that octet rule means really drives the second dairy or the period 2 elements to have a maximum of 8 electrons. Having 8 electrons gives them a very stable structure, low energy state. The reason why atoms bond, of course, is to use each other's electrons, if it's a molecular structure, to achieve a stable octet. All right, and because these are row 2 elements, we know that we can't go beyond the 8. There are some examples of elements beyond that that we could talk about later in another lesson, but here we go. So the basic thing that I like to do in Lewis structures is draw out dots. Remember, Lewis structures are about electrons as point charges, and we're going to draw dots for our electrons. So I know hydrogen, okay, has 1 valence electron, so I'm going to draw that as there. And I know carbon has 4 valence electrons, and you should know at this point, if we're in this kind of a lesson or question, you know valence electrons. So I'm going to put the valence electrons out, okay, and we'll just start with that. So put out all the valence electrons. We know the core electrons are not available to bond. They're too stable, too close to the nucleus. And now nitrogen has 5 valence electrons, so I'm going to start with a bond here with a pair. And again, we could maneuver these around. Lewis structures use the idea that elements are using each other's valence electrons to get a stable amount of electrons. Okay, any case, this is 1, 2, 3, 4, and 5. I tend to put a pair of electrons on the end. Nitrogen has that famous lone pair. Oxygen has 6, okay, and I have 1, 2, 3, 4, 5, and 6. Now I could have put 1 electron here in this pair, if that's what I'm going to start with. Normally that's what I do here, but I am going to not do that, okay, and get rid of that because I know something about oxygen. I know that I could put 6 here and still create a bond here. I know that either by putting an electron here or not, the idea here is oxygen has 7 electrons. We know that oxygen has a valence shell of 6. Okay, it needs 1 more. So putting this electron into this bond doesn't change that. All right, so what I'm trying to do now is manipulate these electrons so that I get a nice octet number 4 or 8 for the carbon, nitrogen, and oxygen. So I'm going to start with this oxygen here. The easiest way to get an 8 for oxygen is to move one of these electrons, okay, right there from the end to this position. Okay. Now I can't move that dot so easy, so I'm just going to erase that there and just move that dot there. Okay, so the reason I move that dot is by moving nitrogen's electron over there. Now I can see by circling, oxygen feels like it has 8 and there's a nice covalent bond there. Okay, and now if I go into nitrogen, if I circle what nitrogen has for its lone pairs and bonding, we can see that 1, 2, 3, 4, 5, 6. Nitrogen only feels 6 electrons. It starts at 5, but it's feeling 6 if I draw that little imaginary circle around the lone pair and all of its bonding electrons. Well, nitrogen has 5 and it wants to feel, you guessed it, 8. Okay, so what I'm going to do here is I'm going to move this electron down to this position and this one down. So I'm going to move these two. Okay, and I'm going to create bonds here. All right, and see if it works. All right, and I got rid of that electron, sorry. So I had these two here and I'm just moving them down. Okay, and I'm going to do the same thing. I'm going to take carbon and I'm going to pair them up. You say, well, why would I want to do that with carbon? Well, first of all, thinking for nitrogen, okay, and we can do this like this. If I think for nitrogen, okay, right now in this orange circle, okay, I've got 1, 2, 3, 4, 5, 6. All right, and so that's not enough. Nitrogen wants to have its 8. So I undo that circle to make things simpler. And now I'm just going to move this X over here and this X, okay, down here. I'm going to pair them up to make a triple bond because that'll give me the 8 that I need there. Okay, so let's go do that. Okay, and so if we check this out, we can see that by circling, nitrogen feels like it has 8. Okay, and now carbon, if I check out carbon's electrons, by sharing these 3 pairs in the pair with hydrogen here, it also feels like it has 8. Okay, and we notice something for hydrogen. And we can put circles in, you don't have to, but sometimes people can see that better. Hey, this oxygen feels like it has 8. Okay, this nitrogen with its bonds and or lone pairs, there's no lone pairs, they're all used up in bonds, feels like it has 8. And this carbon, by sharing, feels like it has 8. And this hydrogen feels like it has 8. And so I have what I call a stable molecular drawing. What I have here is a Lewis dot diagram that works because each atom has either an octet or a filled shell. Of course, hydrogen has the 2. So let's rewrite this to make this nice and neat. Okay, we're going to have a hydrogen, single bond to a carbon, that's triple bonded to a nitrogen. That's single bonded to an O, and it's got 3 lone pairs. Okay, that is one possible structure. Okay, in fact, I'm going to move that. Okay, and there is our one possible structure. Now, let's go find other possible structures. You say, why would there be others? Well, is there another combination here? Okay, that could happen. That creates another stable octet for carbon, nitrogen, and oxygen. And this is where we're getting into other forms that are possible that this structure could resonate into. Resonance, it's important you understand, is not a different form or a different Lewis structure. It's one that blends in to another. I'll talk about that in a second. So the question is, can I write another structure? That's what really this question is about. So if I look carefully, let's see if I can do that. What if I was to take this pair of electrons, and I could take any pair of the oxygen, and I know something about oxygen, it likes to have a double bond to give its formal charge of 0. Okay, now I'm bringing in formal charges here. You not necessarily need them for this question, but it's nice to have this as part of your discussion. Right now the formal charge here is -1. -1 means that oxygen, very simply, is using one of nitrogen's electrons. Hey, remember I took this electron and I gave it to the bond here? 2 of the electrons in the bond, okay, they both came from nitrogen. So I gave one. So this kind of gained one to make this work. Now nitrogen gave one to oxygen, so it's essentially +1. Okay, carbon is using all of its valence electrons, it's 0, and this one is 0. Now, valence electrons, okay, or formal charges I should say, give us these fictitious charges. Okay, They give us these fictitious charges, okay, for help for bookkeeping to tell me what's a better structure. And that's not what this question is, but it really is good to plot that. Now, what's a formal charge? A formal charge, nothing more, is the valence electrons, the electrons you brought to the table to make the structure, minus the assigned electrons. Now, what are assigned electrons? Assigned electrons, okay, this should be a minus sign. The assigned electrons are the electrons that the atom is currently using, half of its bonding and all of its lone pairs. Okay, so we'll talk more about that in a second, but let's go back here. We're going to take this pair of electrons, okay, and we're going to bring it to this bond here. Okay, now that's going to create a double bond, okay, for the O. Now, when it brings 2 electrons here, that still works for oxygen because it'll still be 8. Let me show you what I mean. So if we have an N here, and now we had these 2 electrons, remember one came from the nitrogen, I'm going to put 2 electrons here for this oxygen. It only has 2 lone pairs left. You can use X's or all dots. I'm using the X's and dots to guide whose electrons are moving where. It really doesn't matter in the overall scheme of things. Now, so you can see that by drawing that orange circle, okay, you can see clearly that, looky here, oxygen still has its 8, okay? But what it's going to mess up with is this nitrogen circle of 8. It's now going to have, what, 10 electrons if I keep a double bond and triple bond on this side. So if I maintain the triple bond, nitrogen has what? We'll have 10 electrons. And we know that because nitrogen exists in the second row and this octet rule made famous by Lewis, okay, that's going to exceed the maximum electrons that nitrogen can have, and that is breaking a huge rule, okay, one that's going to make your Lewis structure incorrect. You've got to maintain octets for your second and sometimes third row elements. Talk about that another day. But any case, so getting back to my drawing, okay, so what's going to happen is I'm going to kick out, I think, a pair of electrons to the carbon. If I do it here, that gives me only 2 pairs, okay? And so when I redraw this, what's going to give me is I'll have a dot and an X, a dot and an X, okay? And now I'm going to have a carbon here that has a what? Dot and an X. I'm just plotting where electrons are coming from. It really doesn't matter overall, okay? And then a dot and an X, and I have hydrogen. Okay, now if I do this orange circle here, which is not part of Lewis structure, but we're just kind of, you know, checking our work here, I can see that, hey, that has its 8. And if I check for the carbon, hey, carbon has its 8. Now let's do formal charges just for fun because they are. Take all the valence electrons, which is for oxygen is 6, minus what it's using. That's the assigned. Okay, I should have put a sign there. Okay, so its signed or its lone pairs for half of its bonding, right? We're going to assume that half belong to nitrogen. So you get 2, 4, and then half its bonding. Hey, it's 6. 6 minus 6 is 0. And we know that nitrogen loves to have 0. And we know that formal charges of a 0 really tell us that those are normally the best structures. Okay, so that's a good thing there. And then, of course, nitrogen, well, it has no lone pairs, so half its bonding is 4. And it has a 5 valence, so 5 minus 4 is plus 1. And in here, of course, we have an octet, but there's 2 lone pairs, so I count them, 1, 2, and then half the bonding, 3, 4, 5. So this would be 4 valence minus 5, okay, and this would be a minus 1. You notice the whole thing equals 0. And again, I'm just plotting this for my own sake of trying to draw appropriate structures. Okay, so if we draw out just the, keep out the dots and use these dashes here to clean this up. Okay, remember, this is a Lewis structure and so is this. Here's my other structure. H to a C to a lone pair, okay, to a double bond. Oop, I'm going to keep this consistent. Double bond here. To an N, who is single bonded here. No, I have double bond, right? Double bond there. I can do this. Okay, let's clean this up. And I've got a double bond here, right? And I've got an O with 2 lone pairs. It lost one of the lone pairs to make the extra bond. Okay, and the whole thing is neutrally charged. Remember, +1, -1. It's just that this nitrogen here lost one to the oxygen who gained one to make this work. And in the second drawing, we can say the carbon's what? Formal charge of -1, because it has 5 assigned electrons to make this work, okay, is the idea that it gained one, or a nitrogen gave an electron to the carbon. In this case, we have a nitrogen giving an electron to a oxygen, its valence electron, to make this work. Okay, and that's what formal charges are telling us. Nitrogen lost one to make it work and gained one, but the bottom line is all atoms in these two Lewis dot diagrams, okay, have the octet and are stable. Hydrogens, of course, have there too. So we can think that there's a great possibility that these two structures could resonate. Now, what does resonate really mean? Well, because there's two possible structures that give me an overall, similar, okay, structure, and they're possible, these guys could resonate back and forth. Now, what does that mean? Well, that means that the bond between the N and the O is not a single bond, nor is it a double bond. It's something in between. And this is where I said in the beginning that yes, Lewis dot structures can lead us to some possible structures, but we know there's a limitation. The limitation is that electrons aren't dots, they're waves. So to know exactly if resonance is occurring, we can't answer this question. Or to know if in fact, based on our formal charge rules, which structure is definitely the best and there's only one, or if they're resonating. We would need to know some bond length or bond energy data. We know the bond length between N and O with single bond will be longer than the bond length between an N and double bond. It'll be shorter. So if we can measure this bond length experimentally, we can see if in fact there is resonance. Okay, it's not a single or a double, it might be 1.5. This is not a triple bond between the carbon and nitrogen or a double. It could be something in between. The question is, are there other possible structures? Of course there are, but without experimental evidence, I don't know where to stop. So I'm going to keep going and talking about what other possible resonance structures could exist. Now, it's interesting to note that why can they resonate? Well, I like the fact that these will easily resonate because these two middle carbons and nitrogen are going to be sp hybridized, okay, which means they have unhybridized p orbitals for electrons to be delocalized and move back and forth. Okay, again, that's a lecture for another day. But what could be another structure? Okay, let's keep this going to make some sense of this. So what else can I move? So you notice I moved this pair here and it kicked out this pair. All right, well, what if I add a triple bond here? Certainly possible. Okay, if I maintain my octet rule, so if I take this pair and I move it to make a triple bond, hey, nitrogen would have 10 unless what? One of these pairs kicks out to another position like we did here. So let's draw that. Okay, so we're going to have an oxygen with one lone pair. Okay, and this nitrogen here is now going to have this dot X and two X's. Triple bond. Okay. And of course this pair here is going to move up, so we're going to have a single bond here. And again, we need to do that to maintain the octet rule. Okay. We only can have the maximum number of electrons possible, which is 8 for this second row element, nitrogen and carbon and oxygen. So carbon is now going to have an XO on top, or an X dot, and dot X like we had before on the bottom, and maintain the XX or X dot here for the hydrogen. Okay, so that's what I have here. Let's redraw this. Okay, so we have a hydrogen single bonded to the carbon. That doesn't change in all three. This carbon is going to have two lone pairs. Single bond here. Nitrogen. Okay, and it's going to be triple bonded, which nitrogen loves to do, to the oxygen. Now I don't know about the oxygen with its two lone pairs. Okay, and let's look at formal charges because it's fun to do. Okay, now if you do formal charges, you can use, again, valence electrons minus the assigned, and assigned of course are half the what? Half the bonding electrons in all of the lone pairs. And you can do it like this, kind of cool. Here's the two lone pairs, and let's do half the bonding. And you could see that oxygen is using what? 1, 2, 3, 4, 5. It's got 6 valence electrons. It's using 5, so 6 minus 5 is plus 1. That means it's giving an electron, and there you can see it right there, right? It's giving an electron to nitrogen. What is nitrogen using? Well, nitrogen is using half of its bonding right there. It has no lone pairs. So it's using what? 1, 2, 3. It got that one from the oxygen. That's why oxygen's plus 1, 1, 2, 3, and then 4. So 4 there. Okay, and that's assigned, and of course it has 5 valence electrons. It brings to the party 5 valence electrons, so 5 minus 4 is plus 1. Okay, and of course, okay, looking at carbon, okay, carbon's using its lone pairs and half of its bonding. So looky here, half the bonding here, lone pairs, 1, 2, 3, 4, 5, 6. So it's got 6 assigned, and of course it starts with 4. 4 valence electrons. It brings 4. And it gained 2. And you can see the 2 that it gained if you follow my X and dots. It gained this one and this one. So 4 minus 2 is negative 2. Now in fundamental charge land, we say that negative 2s and anything bigger than a 1 is a bad Lewis structure because this had to gain 2 electrons. And since these are all nonmetals, not good at losing electrons, carbon would have to gain or pull electrons from 2 elements that are what? Very electronegative. So for me, this next structure, which maintains the N as an sp hybrid being linear with no lone pair, okay, would be the other hybrid orbital, but probably very unlikely. And again, I won't know if it's a resonant form unless I look at experimental data, bond length or bond energy. So to me, this is a possible third, okay? And I like to keep the nitrogen as an sp hybrid. Okay, there is certainly, in my opinion, one more structure that we can investigate. Okay, and again, I could write it, but I'm going to leave at these are the 3 that I think are the most probable, even though this third one to me is a little sketchy. Okay, and the next one is having you know, making the nitrogen have a lone pair. So what could happen is, and who knows, this doesn't, again, these are point charges. These are just like our human brains trying to make sense of waves of probabilities, but in any case, we can put this pair here. So we could have a nitrogen with a what? Lone pair. You could have a single bond to an O, right? All right, and then it would have its double bond to the C, okay, and then the C to the H. I'm not a big fan of this Lewis dot diagram for 2 reasons. Carbon only feels 6 electrons here, not its octet, so that to me is not the most stable structure. Okay, and the hybridization is changing. 1, 2, this would be sp3. So I would not consider that to be a viable option, but it certainly could be one if the experimental data of bond length and what? Bond energies show us to be. So these are, in my opinion, the 2 most probable. We could include this third one, okay, for all reasons explained. Hope that helped.